So now let's look at a basic geometric data processing problem of determining intersections among a set of line segments. So it's called the orthogonal line segment intersection search, where the line segments are constrained to be either horizontal or vertical. And so suppose we have a large number of such line segments, and what we want to do is be able to find all places where they intersect. And as we'll see, this extends to a practical problem in a number of situations. In this case, there's 4 places where these lines intersect. So how are we going to be able to determine these intersections efficiently? The natural algorithm, or the naive brute force algorithm, is quadratic in time. So that is, for every line segment, you check whether it intersects with every other line segment. And again, as we know, such an algorithm is not going to be practical for huge numbers of line segments. Just to simplify our code in these slides, and it's often the case for geometric data processing, we have to worry about degeneracies, where lots of things have the same x or y coordinate. And just to simplify the code and to get at the main principles of the algorithms, we're going to assume that all the coordinates that we have are distinct, that we've preprocessed in some way to remove the ones that touch without intersecting. So the method that we're going to look at is the so-called sweep line algorithm. And the idea is to think of a vertical line that sweeps from left to right through the data, and to consider it as every time it hits some line segment as an event where we have to do something. So sweeping from left to right means we consider each x-coordinate as an event. First thing is, if we hit a horizontal line segment, we're going to hit the left endpoint first. And so what we'll do when we hit the left endpoint is insert the y-coordinate of that line into a binary search tree. So we're going to keep track of y-coordinates in a binary search tree. So that's what's happening over in the right there. So now, again, sweep from left to right. What's the next smallest x-coordinate? In this case, it's the line number 1 there, and we'll remember its y-coordinate in a binary search tree. And then 2 and 3. So that's one kind of event that can happen as we sweep from left to right. Another kind of event is that we hit the right endpoint of a horizontal line segment. In this case, we hit the right endpoint of line segment 2. So at that point, the right endpoint of a horizontal line segment, we just remove it because we've processed that line completely. In this case, we didn't find any intersections. So left endpoint, insert the y-coordinate into a BST. Right endpoint, remove that y-coordinate from the BST. So the BST contains the y-coordinates of all the horizontal lines that currently might involve an intersection. And then the third kind of event is what happens when we hit a vertical line segment. Well, in that case, all we need to do is just do a range search for the interval of y endpoints. Any point that's inside that interval is going to represent a horizontal line segment that is an intersection. That's the basic idea behind the sweep line algorithm, to find intersections in sets of horizontal and vertical lines. And it's actually a very simple algorithm, and it's very easy to see that the running time is going to be proportional to n log n plus the number of intersections returned, where there's n horizontal vertical line segments. And it's a couple of ways to implement it. One thing is you could sort according to the x-coordinates, or you could just put them all on a priority queue. And then, so that's going to take n log n for every one of the lines to process them all. Either n to build a priority queue and then log n to take the smallest off each time, or n log n for the sort. And then putting the y coordinates into a binary search tree is, again, n log n, and same for deleting. Each point has to be inserted, deleted. There could be as many n as n in the tree for each one, so it's a total of n log n. And then the range search in the binary tree for each one of the range searches might take log n, might be as many as n, and then there's plus the number of points returned. So that's a quick sketch of the proof of this proposition. And with that 1D range search implementation, we get an efficient n log n 2D orthogonal line segment intersection algorithm.